Hi everyone, in this video we are going to discuss how to predict the three-dimensional arrangement of a molecule in space. So essentially we're trying to predict the geometry of a specific molecule. But in order to do that we need to review two very important pieces of information, essentially fundamentals of how a bond is actually formed. And so the first thing we need to look at, or at least think about, is the attraction between one atom's valence electron to a different atom's nucleus, essentially the protons in the nucleus. And the second thing we need to think about is the repulsion between two atoms' valence electrons. And so essentially, and I'm just going to kind of put it like that, electrons. Essentially what you need to think of is an attraction between one valence electron here to a nucleus or the proton in another atom. And we also need to consider the repulsion between two different atoms' valence electrons. So let's look at a specific example to talk through this. So let's look at diatomic hydrogen. So we know each hydrogen has one proton in its nucleus and it has one valence electron on the outside. And I'm just going to put them kind of randomly here. So the first thing we want to talk about is the fact that this electron right here is very, very much attracted to this proton, in the same way that this electron is very, very attracted to this proton, or the nucleus. So this part right here is an attraction. So these electrons are going to do anything they possibly can to reach the proton, to reach that core, that positive charge of the core of the opposite atom. Now, in the same breath, we kind of need to discuss how these two electrons interact. So I'm going to redraw the picture just for simplicity. So we have an electron here and an electron here. Now, as the electrons start getting closer and closer to each other, all of a sudden they're going to have a repulsion. So the way we would draw that is actually with reverse arrows. And so this would be a repulsion because both of these are negatively charged. And we know enough about magnets that when two things come together and they have the same charge, they repel each other. They don't want to be near each other. These particles absolutely push each other away. And so what we have to do here is battle this attraction against this repulsion. And eventually they find a happy medium or a perfect bond distance. And so what we're going to do today is try to actually use that information to predict the structure of these molecules in space. So let's look at a specific example like we did for a diatomic hydrogen. So if we were to try to do this and actually predict its structure, we start off always by drawing the Lewis structure. So here are our Lewis symbols for hydrogen. We know we are going to just connect the dots. You redraw whenever it looks kind of funky and ugly like that, so you redraw it. Now, no matter how I draw this, this is always going to have a linear arrangement. There's no way I can connect two things without it being a linear bond. And so whenever you have just two atoms, it is always going to have a linear arrangement. So let me ask you a quick question. What do you think the molecular geometry, in other words, the shape, what is the shape of the molecule Cl2? Go. All right, did we get an answer? Hopefully we did, and essentially you just have to go through the exact same steps that we just discussed. So the first thing you do is draw out the Lewis structure. So we know we have two chlorine atoms. They each have 7 valence electrons, so you just draw the 7 dots around it. Then you just connect the ones of the unpaired electrons. We connect here. Always redraw. Please never submit something like that to me. That's just absolutely hideous. We redraw. We see that there's 2 atoms. The only way we could ever describe that relationship or that bond would be a linear geometry. Okay, 2 atoms, always linear. Now, it obviously is going to get much more complicated every single time we add an atom on. So for this course, we're going to do whatever we can to keep it as simple as possible, but please stay with me here because it does get a little complicated. So now, if you have 3 or more atoms, it is crucial, or in other words, you must consider any lone pairs on the central atom. And this is so important. If you can understand this concept right here, this is going to be the easiest subject for you. But just remember, anytime we have 3 or more atoms, you must look at that central atom of your molecule and see if there are any lone pairs. If there are lone pairs on there, then you adjust accordingly. So let's go through some examples here. What if I asked you to draw out the structure for me for SiCl2, okay? So we're going to say silicon's in the center, It has 4 valence electrons, so 1, 2, 3, and 4. Remember, nature always goes for symmetry, so anytime that you can draw a molecule out and maintain symmetry, I would go for it as much as possible. All right, so now draw a line to connect your dots. This would connect, this would connect. That's an ugly picture, so we would redraw it. Okay, always redraw. Just get in the habit of this. And so what I've drawn here is the Lewis structure. So this is the Lewis structure. This is what I would expect you to get from our last unit. Now what we need to do is take it a step further. So it turns out whenever you have a lone pair on this central atom, so right there, that's what I'm talking about, that lone pair requires elbow room. So there are electron-electron repulsions from all of these. So there's a repulsion from this bond right here, because remember the bond has 2 electrons in it. There's repulsions from these lone pairs right here as well. So whenever you have a lone pair on that central atom, think elbow space. They are pushing things around, they are moving things, they require elbow space, they want space. So this actually is not a linear molecule. We would describe it as bent. So if you were to redraw this properly, it would look exactly like this. Okay, so you have, oh geez, I have way too many electrons on my chlorine. There we go. It would look like this. And so you have a lone pair on your silicon, and then you have 2 chlorine atoms with 6 electrons outside of it, and then of course there's 2 right here in the bond. So we would describe this as a bent structure. Okay, and there are specific rules, and we're going to go through them in a second, so you would know how to actually assign that word or assign that geometry. But essentially, it's just a matter of how many lone pairs are on the central atom. So let's look at another example. What about water? H2O. So remember, nature always likes symmetry. Oxygen goes in the center. We have 1, 2, 3, 4, 5, and 6 valence electrons. Our hydrogens go on the outside. Hydrogen only has 1 valence electron. Then we connect the dots. Connect one, connect another. We would redraw that. Actually, that looks fine for a Lewis structure. So our Lewis structure would predict that that's a linear molecule, but that is absolutely not the case. We know that there are 2 lone pairs on our central atom, and so that is absolutely going to affect the structure. And now what water actually looks like in real life is the lone pairs are right next to each other, and this also has a bent structure. So those lone pairs come together, they need space, they need elbow room, and those 2 hydrogens are pushed down to the ground. And so this has a bent geometry. Now, how were you supposed to know that? Well, it's really hard actually without some rules. So let's go through here and assign some rules of everything I want you to follow for this course, okay, for this course. First things first, whenever I ask you to give me a geometry, the first thing you must do is draw out your Lewis structure. You must draw it. Without a Lewis structure, you're not going to get where you need to go. Number 2, you need to determine your number of lone pairs, that's LP, lone pairs, on central atom. So it's the same thing we did with water, and we did the same thing with SiCl2. Now, number 3, you basically apply the chart. Now, I haven't given you the chart. We're going to do the chart in just a second. Okay, so it's simple. You draw your Lewis structure. You determine your number of lone pairs. Then you use this chart to determine the shape. So let's get up this chart here together. First thing, number of atoms on the central atom. So how many atoms are the central atom connected to? Okay, so it's easier said than done, and it will help when we do an example. Next thing, number of lone pairs on central atom. I don't care how many lone pairs are on the external places, so like with our hydrogens before or our chlorines before, I didn't care how many lone pairs were there. I only care about the lone pairs on that central atom. The next thing we want to look at is maybe a picture of it. We want to be able to draw this out, or maybe a drawing. And then the last thing is the actual geometry, or the name. So this is the chart that we're really trying to get to, this last column here. So let's start very, very simple. For our number of atoms on the central atom, let's start if we have 2, and let's just say we have 0 lone pairs on the central atom. So what does that look like? My central atom is always going to be represented by an A. So if we have 2 atoms that are connected to it, so that's 1 and 2, so there's 0 lone pairs on the central atom, this is considered linear. Okay, very simple. Now we're going to methodically go down and just make this bigger and bigger and bigger. So now we're going to keep 2 atoms on the central atom, but this time we're going to add a lone pair. So it's going to look something like this. Here's A, your central atom, 1 lone pair, still connected to 2 atoms, except for this time we have a bent geometry, so it would look like that. Let's move on. What if we have 2 atoms with 2 lone pairs on the central atom. So this would be like water. So we have 1 lone pair here, 1 lone pair here, and now we're connected to 2 different atoms. This also has a bent geometry. Now let's ramp it up, okay? Now we're going to say we're connected to 3 atoms on the central atom. So we'll keep it simple at first. 0 lone pairs. So central atom, we're connected to 3 different things. Here's 1, here's 2, here's 3. 0 lone pairs on the central atom. This has the geometry of trigonal planar. Just have to memorize it, okay? Now let's move on. So now we're going to say we have 3 atoms connected to the central atom, 1 lone pair. So here we go. Central atom, 1 lone pair, and it's connected to 3 things. 1, 2, 3. This one is called trigonal pyramidal. Now, I hear this all the time, pyramidal. No, that's not pyramidal, it's pyramidal. Trigonal pyramidal. All right, moving on. Last one, 4. Okay, so we have a central atom. It's connected to 4 different atoms. We're only going to consider this when it has 0 lone pairs on the central atom. That's it. So this one actually has a really unique structure. So it goes up like this, and then all 3 of these are on the bottom. And this is called tetrahedral. So anytime you see a central atom that's connected to 4 external atoms and has 0 lone pairs on there, it's going to have this shape called tetrahedral, okay? So now, using this information, and you can scroll all the way back up and make sure you're on a video, so go back through, pause through, make sure you have all these notes. Using this information, I want to know what would be the structure of NH3. Go. All right, did we get an answer? Well, in case you didn't, let's work through this together. So we're trying to figure out the structure of NH3. So the first thing you do is you draw out your Lewis structure. So remember, we always go for a place of symmetry. So we're going to put N in the center, and then that has 5 electrons on it, 5 valence electrons. So 1, 2, 3, 4, and 5. Now there's 3 different hydrogens. Each one of these has 1 valence electron. So we draw it over here, connect our dots. 1, 2, and 3. So we have a Lewis structure here that could help us go back to our chart and figure out exactly what shape this is. So let's identify our pieces. We have 1, 2, 3 atoms connected to the central atom. Okay, that was the first piece of information. Now we need to look at the number of lone pairs on our central atom. So we have 1 lone pair on our central atom. So 3 connected to 1 lone pair. You literally go up to the chart. So we're going to go up here. 3 connected to the central atom, 1 lone pair. It would look like this if we redrew it, and the structure is actually called trigonal pyramidal. So if we were to draw out ammonia properly, it would look something like this. It would have a lone pair, and it would have all 3 of the hydrogens sticking down, and this would be called trigonal pyramidal, not pyramidal. All right. We're going to practice a lot with this, so make sure you drill it and drill it and drill it. Do as many examples as you can possibly get your hands on until this feels so easy for you. Good luck. Take care of yourself. Drink water.